Hello. Hi everyone. Welcome to goclasses. Is the audio, volume, video, is everything fine? So let's start in 2 minutes. So let's start now. So in this lecture, we will solve some questions on synchronous counters. We have already seen what is a synchronous counter. This concept we have already seen. Okay, so I will not teach any concept, but we will take some questions, some standard questions we are going to solve in this session. Okay, so this is basically standard question sessions for digital logic. Okay, and if you want the complete playlist of sequence circuits, also the complete playlist of these standard question sessions you can find in the description. Okay, so let's move on now. Okay, so basically this playlist, okay, this digital logic, this complete course link you can find in the description. Okay, you can visit goclasses website. On the goclasses website you can find this digital logic complete course you can find. Okay, so let's move on now. So we have already seen counters, synchronous counters, asynchronous counter, ripple counter. Okay, so these concepts we have seen. Now all these playlist, okay, all these playlist, the link you can find in the description. Okay, all the playlist, like the complete sequence circuit playlist you can find in the description on our goclasses YouTube channel. Okay, also you can notice this digital logic standard question session. This playlist also you can find in the link you can find in the description. Okay, so let's see this question. What is the answer? Tell me. The first question. How many flip-flops are required to make a modulo 32 binary counter? You know what is a binary counter? So binary counter, that is basically, I can say this binary counter, what it will do, it will count from it will count the clock pulses. Okay, it will count from 0, 1, 2 and so on. Okay, and then it will go till 2 power n minus 1. Okay, and then it will become 0. Okay, so this is the definition of binary counter. In a binary counter, if you have n flip-flops, then this binary counter will count from 0 to 1, then 2 and so on. Okay, so it will go till 2 power n minus 1 and then, okay, it will become 0. So this is the binary counter with n flip-flops. So now the question is saying that, now remember this binary counter, if this binary counter has n flip-flops and this is the counting sequence. So if this is the counting sequence, in this counting sequence there are total 2 power n states. Okay, in this counting sequence there are total 2 power n states in this counting sequence. So this counter is also called 2 power n, modulo 2 power n counter. Okay, this is also called modulo 2 power n counter. Okay, now the question is saying that you want modulo 32 counter. Okay, so you can notice with 5 flip-flops. So if you have 5 flip-flops, then using 5 flip-flops, what you can do, you can create 2 power 5 counter. Okay, modulo 2 power 5 counter you can create. Okay, so you can notice, so we need total 5 flip-flop. Is this point clear? Very simple. What is a binary counter? Binary counter is simple, very simple. That binary counter will count the clock pulses. It will count the clock pulses. Okay, so you can notice like it is counting the clock pulses. In every clock pulse, what will happen? In every clock pulse, it will increment. In every clock pulse, it will increment. So I can say it is counting the clock pulses, correct? I can say, for example, if the value is 3, if the state of this binary counter is 3, then what that means? It means that total 3 clock pulses it has seen. Okay, total 3 clock pulses it has seen. So you can notice this binary counter, what it does, this binary counter counts the clock pulses. Okay, this binary counter, okay, so this binary counter, what it does, it counts the clock pulses. It counts the clock pulses. Okay, this is what it does. Remember, because you can notice it will start from 0. This is the initial state. From this state, what will happen? If a clock pulse comes, okay, then what will happen? It will go to state 1. If another clock pulse comes, if another rising edge comes, if your flip-flops are positive edge triggered, okay, I'm assuming that your flip-flops are positive edge triggered. So if you assume that flip-flops are positive edge triggered, then what will happen? On every positive edge of the clock, okay, so you can notice the state will change. Now you can notice initial state is 0. On every positive edge of the clock, the state will increment. Okay, you are in state 1. On every positive edge of the clock, the state will increment. So you can notice that if you are at this state, okay, if you are in this state, what it means? It means that total 3 clock pulses you have seen. Okay, like this, and so on, and then finally 2 power n minus 1, and then finally, okay, again it will go to state 0. So this is called modulo 2 power n counter. Okay, so very simple. So for this question answer will be 5. Using 5 flip-flops you can create, remember, using 5 flip-flops you can create modulo 2 power 5 binary counter you can create. Okay, let's move on. Let's see this question. What is the answer? For this question, what is the answer? Synchronous counter. Okay, this is the question. So let's look at this. So synchronous counter. So what this is saying, that synchronous counter eliminates the delay problem encountered by asynchronous counter. You know what happens in asynchronous counter? This we have already seen. What is the problem with asynchronous counter? What is the problem with asynchronous counter? Do you remember? What is the problem with asynchronous or ripple counter? What are the major problems? What are the major problems with asynchronous or ripple counter? The first major problem is that is your transient states. Okay, this is the first problem. Transient states. You get transient states. For example, if you have a binary counter, let's assume you have a binary up counter. Let's assume you have a binary up. Okay, binary up ripple counter you have. Okay, so let's assume this binary up ripple counter you have. Then what will happen? Tell me. In this binary up ripple counter, when you go from this state, for example, let's assume this 3-bit. Let's assume this is 3-bit binary up ripple counter you have. Now from this state, or maybe I can say from this state, what will be the next state? If this is your current state, what will be the next state? Tell me what will be the next state. Okay, so this is your binary up ripple counter. So in this binary up ripple counter, if this is your current state is 3, state 3. So the next state will be 4. But you can notice what will happen here. You can notice this will happen, that in this ripple counter what happens, first this LSB will change. Okay, so first this LSB will change. Okay, so this is a transient state. For a moment this state you will get. Okay, then what will happen? So first this LSB will change. Then what will happen? Then this will change. Okay, then this will change. And then finally what will happen? This will change. Okay, finally this will change. So you can notice that in this ripple counter, in this binary ripple counter, we are getting the transient states. Yes or no? We are getting the transient states. We are getting the transient states. So this is the idea. Okay, now one more thing, let me ask you. If you go from this state, what should be the next state? Okay, in a 3-bit binary up ripple counter, from this state, what will be the next state? And how many transient states will be there? Tell me. Okay, this is your current state. Now I am asking, in the 3-bit binary up ripple counter, okay, if this is your current state, then how many transient states will be there? You know the next state. The next state will be, this is state 2, so the next state will be 3. How many transient states will be there? Like you can notice here you have 2 transient states. Okay, from this state you should go to this state, but for a moment you will get these states for a moment, because first LSB will change. Then okay, so first this LSB will change, then this middle bit this will change, and then finally this MSB will change. So 2 transient states we got, I can say. Okay, I can say that total 2 transient states we got in this. Now my question is that, okay, so if your state in this 3-bit in this 3-bit binary of ripple counter, if your state is 0 1 0 means 2, so next state must be 3. So how many transit states will be there? There will be no transit states, okay, because you can notice only one bit is changing. Because only one bit is changing, so that is the reason there is no I can say transient states. So I can say here there is no transient states. Here there is no transient states. But anyway, the point is very simple, that in asynchronous, in ripple counter, this is a problem. In ripple counter, this transit state, this is a problem. Okay, because in a ripple counter, what happens? In a ripple counter, first LSB will change. Okay, so this LSB will change with every clock cycle. Okay, this LSB, what it will do? This LSB, this will change with every clock cycle. With every clock cycle, this LSB will change. And you can notice when the LSB is changing, then MSB will change. Okay, so like this. So like this will happen. So first LSB will change with every clock cycle. First LSB will change. Okay, and then you can notice when the LSB is changing, then this MSB will change. Okay, so this is a problem in a ripple counter. What is the another problem in ripple counter? Tell me, what is the another problem in ripple counter? Another problem of ripple counter, what is that? That is your, I can say, propagation delay. Okay, that is your, I can say, propagation delay. Okay, that is your propagation delay. This is another problem. This, I can say, cumulative propagation delay, because the last, okay, this is the cumulative propagation delay. This is the problem. What this means cumulative? Why I am calling it cumulative propagation delay? What is the reason? Why this is a problem? Cumulative propagation delay. Because you can notice that if you have this ripple counter, if your ripple counter is this, then you can notice that here, okay, on the first flip-flop, this is your LSB flip-flop. On this first flip-flop, the clock will apply. Okay, so this will change state in every clock. But you can notice that when this LSB is changing the state, then this will change the state. Okay, then you can notice the output of this flip-flop is acting as clock for this flip-flop. Okay, the output of this flip-flop is acting as clock for this flip-flop. So here what will happen? Here you can notice the propagation delay is increasing. Okay, the propagation delay is increasing. So I can say that for the last flip-flop, what will be the propagation delay? So this, for if you have n flip-flop, let's assume you have n flip-flop, then you can notice for the last flip-flop, for this last flip-flop, what will be the propagation delay? Here tell me what will be the delay. Here tell me what will be the delay. The propagation delay will be n multiplied by, okay, that will be n multiplied by TPD. Okay, this TPD, what is this TPD? This TPD is one flip-flop propagation delay. Okay, so this is propagation delay of a flip-flop. Okay, so this is the idea. So you can notice that here the propagation delay will be TPD. Here propagation delay will be 2 TPD. Okay, here propagation delay will be 3 TPD, and so on. So that is the reason we call it cumulative propagation delay. Okay, this is the problem, cumulative propagation delay. Please tell me, is this point clear? Let me know. Is the audio, video, visuals, is everything clear? Is the video quality clear? Let me know. Audio, video, volume, video quality, audio quality, please tell me, is everything clear? Just give me a minute. Okay, so let's see. So these are the problems with asynchronous ripple counter. Now this is our question. So tell me what is the answer. Synchronous counters, okay, these synchronous counters, they don't have problem of transient states. So in these synchronous counters, there is no problem of transient states and there is no problem of cumulative delay. So you can notice synchronous counters eliminate the delay problems, okay, encountered by asynchronous counters. Because what is the reason? Tell me what is the reason these asynchronous counters, what is the reason these ripple counters have this cumulative delay problem? Okay, in ripple counters, these are the two problems. These are the these are the two problems in ripple counters. What are the two problems? The first problem is transient states. This is the first problem, transient states. Okay, this is the first problem. And the second problem is cumulative delay. Okay, the second problem is cumulative delay. This is the second problem, cumulative delay. So these are the two problems with ripple counters, and the reason of these two problems that you already know, because you can notice the same clock is not applied to all the flip-flop. Okay, the output of this flip-flop is working as clock for this flip-flop. Okay, the output of this flip-flop is working as clock for this flip-flop. Okay, so like this it is happening. This is the problem. But you can notice in the synchronous counter, these problems we don't have. In synchronous counter we don't have these problems. So finally answer will be very simple, that these problems are not in synchronous counter, because the input clock pulses are applied simultaneously to each flip-flop. So the answer will be option D. Okay, the input clock pulse, the same clock is applied to all the flip-flops simultaneously. So all the flip-flop will change state simultaneously. Okay, they are not waiting for one another. So this is the idea. Now tell me about this question number 3. Question number 3. What is the difference between combinational logic and sequential logic? What is the difference between these two? So you can notice in sequential logic, the current output will depend on past latest input and also on past output. Okay, so this is the idea. So I can say that for this question, what will be the answer? So in this question, the first option is saying that the output of both combinational and sequential logic circuit depend not only on present values of their input signals but on the sequence of past inputs. This is wrong. This statement, this option is wrong. Why this option is wrong? Because in the combinational circuit, the output will depend only on the current inputs. Okay, so this statement is wrong. You can notice this statement. So this statement is wrong. Next, why this statement is wrong? Because in combinational circuit, I can say the output. Okay, in combinational circuit, you can notice that the output will depend only on the latest input. It will not depend on the past inputs. Okay, so this statement option A is wrong. Next, timing pulses trigger both combination and sequential circuit. This is also wrong, because timing pulses, like in combination circuit we don't have the clock. Okay, we don't have the clock. Next, neither circuit is triggered by timing pulses. This is also wrong. In sequential circuits we have the clock. We have the concept of clock. Next, the output of combinational logic circuit depend only on the present value of their input signal, while the output of this sequential circuit depend on the present values of their input and also the sequence of past inputs. This option is correct. So the answer will be option D. Okay, so very simple. Now tell me the answer for this question. These are some simple questions. What is the answer for question number 4? So this we have already seen. This synchronous counter. This synchronous counter will eliminate the problem of cumulative delay. In this synchronous counter we don't have the cumulative delay problem, because this ripple counter has the cumulative delay problem, and the reason is very simple, that input clock pulses, I can say the reason is very simple, that input clock pulses are applied simultaneously to each flip-flop. Next, what is the answer for this? How many different states a 3-bit asynchronous counter has? So if you have a 3-bit asynchronous counter, means there are 3 flip-flop. Okay, it simply means there are 3 flip-flop. Okay, each flip-flop can have 2 states, either 0 or 1. A state of any flip-flop can be 0 or 1. So every flip-flop can have 2 states, 0 or 1. So finally I can say that a 3-bit asynchronous counter, how many different states are there? That will be 2 power 3. So answer will be 2 power 3. Next. Next. You are implementing a state machine. That is designed to have 15 states. You want total 15 states. Then how many minimum number of flip-flops are needed? So you want 15 states, then definitely at least 4 flip-flops we need, correct? At least 4 flip-flops we need. So I can say answer will be option B. Okay, using n flip-flop, remember, if you have total n flip-flop, using n flip-flop total, how many states you can have? Using n flip-flop, at most 2 power n states you can have. At most 2 power n states you can have. Using n flip-flop, at most 2 power n states you can have in your circuit. Okay, so this is the idea. So here you can notice, if you want 15 states, then at least 4 flip-flop you need. So the answer will be 4. Tell me the answer for this question. What is the answer? So in this question we have a JK flip-flop. Okay, the question is saying that there is a JK flip-flop with J equal to 1, K equal to 1, and this is the clock input. The clock has 20 kilohertz frequency. Then the Q output is. So you can notice in a JK flip-flop what happens when J equal to 1, K equal to 1. So it happens. We have already seen. This is your JK flip-flop. So this is the JK flip-flop. Now in this JK flip-flop, when this J equal to 1, K equal to 1, in this situation, let's assume there is a clock. Let's assume this JK flip-flop is positive edge triggered. So here you have a clock. Now this clock can be anything. Okay, this clock can be anything. For example, this clock can be like this. Okay, for example, this clock can be like this. Is this a, okay, tell me, is this clock uniform? For example, can I say this clock is a square wave? This clock. Okay, this clock, is it a square wave? No, this clock is not a square wave. So let's assume this clock has frequency. Okay, let's assume this clock has frequency f hertz. Okay, f hertz, this is the frequency. Then what will be the output? The output frequency will be f by 2. This we have already seen. Okay, so if this frequency is f, then the output, first of all, output will be like this. Okay, remember, output will be a perfect square wave. Output will be a perfect square wave. Okay, so the output will be a perfect square wave and the frequency will be f by 2 hertz. This will be the frequency. Okay, so this is the idea. So these are the benefits. These are the benefits you can notice. So if the clock for this JK flip-flop, when J equal to 1, K equal to 1, then I can say that if this clock has frequency f hertz, then the output will have frequency f by 2 hertz. Also remember the output will have perfect square wave. This output will have perfect square wave. You can notice the input is not a perfect square wave. Okay, but you can notice output is a perfect square wave. Means this output has duty cycle. This output has duty cycle of, so remember this has duty cycle of, okay, I can say this has duty cycle 50%. So the answer will be like this. Okay, answer will be that this has frequency 20 kilohertz. So the output will have 10 kilohertz square wave. That will be a perfect square wave. Next, what is the question? The next question, what is the disadvantage of SR flip-flop? In SR flip-flop, we know that S equal to 1, R equal to 1. For this input combination is forbidden. Okay, I can say this input combination is invalid combination. So this is the idea. This input combination is forbidden. So I can say it has invalid state. So the answer will be option B. Okay, let's see this question. What this question is saying. In the question it is saying that a synchronous counter's speed is limited by propagation delay of each flip-flop. Is that true? Is that true? A synchronous counter's speed is limited by the propagation delay of each flip-flop. So this statement is wrong. This statement is wrong because it happens in the ripple counter. In the ripple counter this happens. Remember, in the ripple counter this happens. Okay, so in a ripple counter this happens. Now this we already know. This is very important point. Let's assume on one hand you have let's assume you have n flip-flop. Let's assume you have n flip-flop. No additional combination circuit. Okay, let's assume you have n flip-flop and there is no additional combination circuit. Let's assume there is no additional combination circuit. There are n flip-flop. In this situation, because you have n flip-flop, in this situation, what will be the frequency of clock in the ripple counter? Tell me, what is the maximum frequency of the clock in ripple counter and what is the maximum frequency of the clock in synchronous counter? Okay, let's assume every flip-flop, each flip-flop propagation delay is t. Let's assume each flip-flop propagation delay is t. Let's assume that is t. Okay, so I am assuming that each flip-flop propagation delay is t. Okay, so let me assume. So you can write somewhere here. Each flip-flop has propagation delay t. Okay, now you tell me. So if you have ripple counter, in ripple counter, what should be the clock? I can say what should be the clock time period? What should be the clock time period? What should be the clock time period? This must be greater than equal to n multiplied by t. Okay, this must be greater than equal to n multiplied by t. And in synchronous counter, what should be the clock time period? What should be the clock time period in synchronous counter? That should be only greater than t. It does not depend on number of flip-flop. It depends on number of flip-flop. Yes or no? It depends on number of flip-flop. It depends on number of flip-flop, but it does not depend on number of flip-flop. So if you have n flip-flop, there is no additional combinational circuit. And let's assume every flip-flop has propagation delay equal to t. Then in a ripple counter, the clock time period will be greater than equal to nt. It will depend on number of flip-flop. Remember, this is your number of flip-flop. You can notice here it does not depend on number of flip-flop. Also, I can say what is the maximum frequency. What is the maximum frequency of the clock? What is the maximum frequency of the clock? What is the maximum frequency of the clock? So maximum clock frequency, what is that? Maximum clock frequency, what that will be? So you can notice here the maximum clock frequency will be less than equal to n multiplied by t, and here it will be less than equal to 1 by t. So you can notice it does not depend on number of flip-flop. It depends on number of flip-flop. Okay, so the maximum frequency is limited by number of flip-flops. Can I say that in a ripple counter, the maximum frequency is limited by number of flip-flops. Okay, so this is the idea. You can notice in a synchronous counter, speed is limited by the propagation delay of each flip-flop. This statement is wrong. Okay, this statement will be true for ripple counter. Okay, this statement will be true. Remember, this statement will be true for ripple counter. For ripple counter, this statement will be true. Okay, let's see the next question. The counters are also called frequency multipliers. Counters are also called frequency multipliers. No, they are called frequency dividers. Yes or no? They are called frequency dividers. These dividers would be correct. Okay, they are called frequency dividers. For example, your T flip-flop. This is a, I can say, if you have a T flip-flop, this is your T flip-flop, T equal to 1, then you can clearly see if your input has, if your clock has f hertz frequency, then the output will have, okay, f by 2 hertz square wave. Okay, square wave. Okay, so you can notice, so I can say frequency divider. That is the reason this T flip-flop is called frequency divider. Okay, these are frequency divider. So T flip-flop is called frequency divider by 2. Okay, so this is the question. So counters are called frequency multipliers. This is wrong. Actually, these are called frequency dividers. Next, a mod 10 counter will count up to binary number 9. This is correct. Okay, this is correct because a mod 10 counter. Okay, a mod 10 counter, what it will do? A mod 10 counter means total 10 states are there. Okay, means total 10 states are there. So this is correct. To build a mod 4 counter, we need 2 flip-flop. Okay, mod 4 counter means total 4 states we need. Mod 4 counter means total 4 states we need. So I can say we need 2 flip-flop. This is also correct. Using 2 flip-flop, you can create 4 states. Next, the maximum binary count of mod 64 counter. The maximum binary count of mod 64 counter, that is 63. Yes or no? That is actually 63, not 64. Okay, so this statement is wrong because remember the maximum binary count. Okay, the maximum binary count of a mod 64 counter. You have a mod 64 counter. In a mod 64 counter, the maximum binary count can be 63. You cannot have 64. Okay, so this is statement 5th. This is wrong. Okay, because the maximum binary count will be 63. Okay, so this is the idea. Now you can notice this statement is also wrong. Now let's move on. Tell me about this one. Okay, true or false? A synchronous counter is one where all the stages, okay, a synchronous counter is one where all the stages of the counter trigger together. Yes, this statement is true. Synchronous counter eliminate the cumulative flip-flop propagation delay. This problem, who has this problem? Tell me. Who has this problem? Cumulative flip-flop delay. This problem is in the ripple counters. This problem is there in the ripple counters. Ripple counters have this problem. Okay, so this is the problem with ripple counters. Or I can say ripple counters have this problem. Synchronous counter does not have this problem. I can say, okay, you can notice synchronous counter eliminate the cumulative flip-flop delay seen in ripple counter. Yes, this is correct. So this statement is correct. Next, a universal shift register. So this we have already seen. What is a universal shift register? This we have already seen. The implementation we have seen. So a universal shift register will accept parallel input, correct, bidirectional serial load, internal shift features. So all these things are correct. In a universal shift register, you have the facility to shift left, shift right, okay, parallel input, parallel output. So all these facilities you have in a universal shift register. Next, parallel load, okay, parallel load. So parallel input, you can notice parallel load of a shift register means each flip-flop is loaded with data one at a time. No, this is not correct. Okay, because parallel load simply means that you are giving the parallel inputs. You are giving the parallel inputs. So you are loading the data in parallel. So you can notice this statement is wrong, because this statement is saying that we are doing one at a time. So this statement is wrong. Okay. Now let's see this question. The next question is from okay. So let's see this question. This is question number 5.8 in digital design by Maurice Mano. Okay, in the 5th edition. So this is a very nice question on sequence circuit, on synchronous sequence circuit. Let's check it out. Let's check this question. So what this question is asking? In this question, you can notice that this counter is given to you. Okay, and this is a synchronous counter. Can you see this is a synchronous counter? Why this is a synchronous counter? Because you can notice same clock. Okay, we are applying the same clock to both the flip-flop. There are two T flip-flop and both the flip-flop are, okay, I can say they are operated by the same clock. The same clock, okay, you can notice they are operated, these two flip-flop, they are operated by the same clock. Okay, so that is the reason this is a synchronous circuit. Okay, now you can notice there are two T flip-flop. Let me call it TA, let me call it TB. Okay, let me call it TA. Let me call it TA and let me call it TB. So this is what I am calling. Remember, I am calling it TA. This I am calling TA and this I am calling TB. This is what I am calling. Okay. Now let's see. So how to do the analysis of synchronous sequence circuit? This we have already seen. How to do the analysis? If you have a synchronous sequence circuit, then how to do the analysis? That is very easy. Okay. The idea is this. Okay. So let me first write the idea. So what is the idea of analysis? Okay, the idea is very simple, that you have a state. You have a state. This is your current state. So from current state, you try to find out what will be your next state. Okay, so from current state, you try to find out what will be your next state. Now what you do from current state, what you will do from current state, you will find out what are the flip-flop inputs. Okay, so you have current state. From this current state, first you will find out what are the flip-flop inputs. Okay, you will find what are the flip-flop inputs. Then from that you can find the next state. Okay, this is the idea. I hope this idea is clear. So this is the idea of analysis of synchronous sequence circuit. Now in this question we will do this. So how many states are there? You can notice there are two T flip-flop. So first you tell me what is TA. Tell me quickly, what is TA? What is TA? TA, what is that? So you can notice in this TA we have this is A. Okay, so you can notice this is A. So TA is equal to A. And what is this A? This is the state of T flip-flop. Yes or no? What is this A? This is, I can say, state of TA flip-flop. This is the state of TA flip-flop. Okay, and you can notice this is your B. Similarly, this is B, and similarly this is A bar. So what is TA? First you tell me what is TA. TA is A or B. This is TA. And what is TB? Tell me TB. TB is A bar or B. So you can notice this is TA, this is TB. So we got this. Now what we will do? This is the idea we will do. So you are in the current state. From the current state you will find what is the next state. This is what you are going to find. Okay. So your current state is basically, I can say, your current state is A. Okay. And this B, this is your current state. And what is the next state? Next state means A next, B next. Okay, this is your next state. And you can notice these are the flip-flop inputs, TA, TB. These are the flip-flop inputs. So here what will happen? Your current state, how many? Okay, so there are total 4 states are there. 0, 0, 0, 1, 1, 0, 1, 1. Now you can notice if you have this A, B. Okay, if this is your current state. Remember, this is your current state. Remember, this is your current state. and you can notice this is your next state. This is the next state, and these are the flip-flop inputs. You can notice these are the flip-flop input combinations. So here what will happen? So this is your current state. Now we will try to find from the current state, we will find what is the next state with the help of flip-flop inputs. So from the current state, we will find what are the flip-flop inputs, and then using from these flip-flop inputs, we can find what will be the next state. So you can notice if your A comma B is 0 0, then what is TA? TA is A or B. Okay, remember TA, that is A or B. That is A or B. And what is TB? TB is A bar or B. TB is A bar or B. Sorry. So TB is A bar or B. You can notice TB that is A bar or B. Okay. A bar or B. So this will be TB. Now, after this what to do? After this what to do? Now you have very simple. So you can notice if your T is 0, if your T is 0, then what will be the next state? Tell me. If your T is 0, if your TA is 0, this TA is 0, then you can notice the next state will be same as the previous state. And here TA is 1. So the next state of this flip-flop will toggle. It will become the complement of the present state. Next state will be the complement of the present state. Okay, you can notice next state will be the complement of the present state. Now similarly you can notice that here TB is, this TB is 0. So when TB is 0, then the next state will be same as present state. So in this situation, you can notice the next state of this TB flip-flop, the next state will be same as the present state. Okay, and for the remaining, and you can notice for the remaining, for these remaining, okay, for these remaining what will happen? For these remaining, because your TB equal to 1, so for this TB flip-flop what will happen? The next state will be complement of the present state. So next state will be complement of the present state. Okay, so this is the idea. Is this clear to everyone? Now we have, finally we got our state diagram. So what is the state diagram? What will be the state diagram? So from this question, what we got the state diagram? State diagram is very simple, that this is your 0 0. Remember here I am assuming that this is A, this is B. Okay, so MSB, I am assuming A is the MSB. Okay, and I am assuming that B is the LSB. This B I am assuming LSB. So from this state 0 0, where are you going? You are going to 0 1. You are going to state 0 1. From this state 0 1, you are going to 1 0. Okay, you are going to 1 0. And from this state 1 0, you are going to 0 0. Okay, and you can notice from this state 1 1, you are going to 0 0. From this state 1 1, you are going to 0 0. This is the state diagram. Okay, this is your state diagram. Now you tell me, what is the modulus of this counter? What is the modulus of this counter? For this counter, what is the modulus? Remember, this is your repeating sequence. Remember, this is your repeating sequence. This is your repeating sequence. So this is the repeating sequence. So I can say this is the counting sequence. Remember, for this counter, this is the repeating sequence. We can also say this is the counting sequence of this counter. Okay. So finally, I can say this is a mode 3 counter. Mode 3 counter, because in the counting sequence there are 3 states. In this repeating sequence, there are 3 states. So that is the reason this is a mode 3 counter. Okay, so this is a mode 3 counter, and you can notice in the counting sequence, if they ask you what are the states in the counting sequence, so what are the states in the counting sequence? These are the states in the counting sequence. Okay, so these are the states in the counting sequence. You can notice from 0 to 1, 1 to 2, and then from 2 to 0. So you can say that this is a mode 3 counter. This is a mode 3 counter because in the counting sequence there are total 3 states. Okay, so we have the state diagram. So this state diagram we have created. This is the analysis of this. Now you can also find out what is the next state. You can also try to find out what is the next state equation. So they can ask you what is the next state equation. This also they can ask you what is the next state equation. Next state equation, this also they can ask you. So next state equation means, remember, next state equation, what that means? That means you have to find out what is A plus. You also have to find out what is B plus. This is what you have to find out. Okay, in terms of what? In terms of your present state, and in terms of your present state, that's it. So I can say your next state, we need to find out what is the next state. This next state equation in terms of present state. Why in terms of present state? Because there is no external output. there is no external input in this circuit there is no external input, correct? Is there any external input? Tell me, is there any external input in this circuit? Is there any external input in this circuit? Do we have any external input? Is there any external input? No, there is no external input in this circuit. In this circuit you can notice the state of the flip-flop. This is the state of the flip-flop. Remember, this is the state. Please understand, this is not the, okay, this is not an input, this is not an external input, this is state of TB flip-flop. This is state of TB flip-flop. So you can notice in this circuit there is no external input. So that is the reason I can say that this next state will depend on the present state. This next state will depend on the present state. So now finally we can write the equation. So what is A plus? So from this truth table you can find the A plus. So tell me, what will be A plus? From this truth table, what will be the A plus? What this A plus will be? What this A plus is going to be? So this A plus will be A bar B. Okay, correct? This A plus will be A bar B. And what this B plus will be? What this B plus will be? Tell me what this B plus will be. This B plus will be A bar B bar. Okay, this will be A bar B bar. So you can notice, I can say that this A plus, this will be A bar B, and this B plus will be A bar B bar. This is your next state equation. Is this clear to everyone? So this is the complete analysis of this previous question. Okay, let's move on. Let's do the analysis of this circuit. Did you do this? This question, did you do? What is this circuit? This counter. This counter is what type of counter? What is the modulus of this counter? Tell me. What is the modulus of this counter? This is my question. My question is, what is the modulus of this counter? These are the clear. Okay, these are the clear. So let me call it R. Let me call it R. Let me call it R. R means clear. Okay, so let me call it R. R means clear. So these are the clear. This is your clear input. Okay, so what is the modulus of this counter? Can anyone tell me? Did you try this question? I gave you this question as a homework. So this is your clear inputs. These are the clear inputs. You can note this is the clear inputs. Okay, anyway, so let me give you the analysis. Very simple. Okay, let's do the analysis. So first of all, you tell me, okay, there are total 3 flip-flop. We have total 3 flip-flop. Is there any external input? Is there any external input? Tell me, is there any external input? Is there any external input? Do we have any external input? Okay, so there is no external input. In this question, we don't have any external input. Okay, what we have this T1, we have this T2, and we can call it T0, we can call it T1, and we can call it T2. So total 3 flip-flop we have. And you can notice there is no external input here in this circuit. We don't have any external input. Okay, so this is your circuit. Now in this circuit, you tell me what is T0? T0 equal to 1, that is fixed, correct? So you can notice this will happen. What is the idea? The idea for analysis, you know the idea. Okay, idea of analysis of synchronous circuit. Of synchronous circuit. What is the idea of analysis? So the idea of analysis is very, very simple. You are in the current state. You are in the current state. From this current state, what will be your next state? This is what we have to find out. We have to find out from this current state what will be your next state. And how to do that? Very simple. First you will find flip-flop inputs. Okay, first you will find out what are your flip-flop inputs, and then from that you will find out what is the next state. Okay, so like this is the idea, remember. So once you understand this idea, you can solve this question very easily. Remember, there are 3 flip-flop. So I can say your current state will be like this, Q0, or maybe I can say Q2, Q1, Q0. This is your current state. Okay, and your next state will be, I can say Q2 plus, Q1 plus, Q0 plus. This will be your next state. And there are 3 T flip-flop, T2, T1, T0. Okay, we have 3 T flip-flop. Now you can notice this T0, this is fixed equal to 1. This T0, this is fixed equal to 1. This is fixed equal to 1. And this T1 is equal to Q0. You can notice this T1 is equal to Q0. Next, after that, so this T1, this is equal to Q0. After that, this T2 is equal to Q1, Q0, Q1. This T2 is equal to Q0, Q1. Okay, this T2, this is equal to Q0, Q1. So this is the inputs. Okay, this T2 is equal to, you can notice this T2 is equal to Q0, Q1. Okay, very simple. Now you tell me, okay, one more thing that is interesting. Here one more thing is interesting. What is that? What is that? So when this clear input will be, okay, when this clear equal to 0, then in this situation, all the flip-flop, they will clear. Yes or no? When the clear input is 0, okay, so when this clear input is 0, when you make this clear input is 0, when clear, okay, means clear equal to R equal to 0, then all flip-flop, then what will be the state of this counter? Then state of this counter, what will be the state of this counter, tell me? What will become the state of this counter? The state of this counter will become 0, 0, 0. This will become the state of the counter. So when this clear input of all the flip-flop, so when this clear input becomes 0, because the clear input is active low. So when the clear is 0, then it will do its work. So when the clear is 0, then in this situation, the state of the counter will become 0, 0, 0. So when the state of the counter will become 0, 0, 0, when clear will become 0, tell me. When this R equal to clear, when this clear will become 0, when this clear will become 0, this clear will become 0 when Q0, you can notice this is your Q0, Q2 bar. Okay, this R is equal to, remember this R, if you understand what is this R, so this R is basically, I can say Q0, you can notice this is Q0, Q2, this is Q0, Q2 bar. Okay, so when this R will be 0, when this R will be 0, I can say that this R will be 0, I can say this R will be 0, it simply means that Q0 is equal to 1 and Q2 is also equal to 1. So both are 1. When Q0, Q2, when both are 1, then the next state will be what? Then the next state will be 0, 0, 0. Okay, so this is the idea. So let's see this. So the table will be like this: 0, 0, 0, 0, 0, 1, 0, 1, 0, 0, 1, 1, 1, 0, 0, 1, 0, 1. Okay, now you tell me. So when Q2 and Q0 are 0, when Q2, Q0 are 1, when Q2, Q0 are 1, when both are 1, then what will happen? When Q2, Q0 are 1, you can notice, when they become 1, then what should be the next state? Tell me what should be the next state? When both are 1, when this Q2, Q0, when both are 1, then what will be the next state? When they both are 1, then the next state will be 0, 0, 0. Correct? The next state will become 0, 0, 0. Okay? In other situation, everything is fine. In other situation, so in this situation, the next state will become 0, 0, 0. Okay, you can notice. So if any time, okay, like 1, 1, 0, then also it will become 0, 0, 0. If you take 1, 1, 1, then also it will become 0, 0, 0. Okay, so you can notice that whenever this Q2, Q1, Q2, Q0 is equal to 1, 1, then what will happen? The next state will become 0, 0, 0. Okay. Now in the remaining, you can notice this T0 is 1. You can notice that T0, look at the T0. So this T0 is basically 1. And because this T0 is equal to 1, so what will happen? Because this T0 is equal to 1, so what will happen? Whenever this T0 equal to 1, then for this, the output of this T0 flip-flop, okay, it will toggle in every clock cycle. Okay, because T0 is equal to 1, so the output of this T0 flip-flop, the next output of this T0 flip-flop, that will be the complement of the present output of this flip-flop. So I can say it will be 1, 0, 1, 0, okay, 1, 0. Next, similarly, this T1 equal to Q0. Remember this T1, this is equal to Q0. This is equal to Q0. So I can say that when, in this situation, what will happen? When this T1 equal to 0, okay, next state will be same as the present state. When this T1 equal to 1, next state will be complement of the present state. When this is 0, this will be, when this is 0, this will be same, this will complement, this will same, and this will complement. Okay, next. So next, what is this T2? T2 is Q2, Q0, Q1. Okay, T2 is this. So your T2 is actually this. This is the T2. This is the T2. So you can notice here, only in this situation, the next state will complement. Okay, in all the other situations, I can say the next state will be like this. Okay, so this is your circuit. So tell me, what is this circuit? Can anyone tell me? In this circuit, what is happening? So from this 0, where are you going? From this 0, you are going to state 1. From this 0, you are going to state 1. From state 1, you are going to state 2. From state 2, you are going to state 3. From state 3, you are going to state 4. From state 3, you are going to state 4. from state 4, you are going to state 5, from state 5 you are going to state 6, and from state 6 you are going to state 0. Okay, so is this point clear? Sorry, in this question some mistake we have done. Sorry, so this will be, okay, from 5 you will go to 0. Okay, so actually from 5 you will go to 0. From this state 5 you will go to state 0. Correct? Yes or no? Is this clear? Because from this state 5, once you come to this state 5, okay, then you will go to state 0. From this state 5 you are going to state 0. Tell me, is this point clear? From this state 5 you are going to state 0. Now tell me, so what is the modulus of this counter? What is the modulus of this counter? Tell me. For this counter, what is the modulus of this counter? What is the modulus of this counter? So you can notice very simple that from 5 you are going to 0. Okay, so from 0 you are going to 1 to 2, 3, 4, 5, and then from 5 you are going to 0. So what is the modulus of this counter? My question is, what is the modulus of this counter? So can I say answer will be mod 6? Can I say this is mod 6 counter? Can I say this is mod 6 counter? Can I say this is mod 6 counter? Can we say this is mod 6 counter? And here the answer is wrong. Okay, this answer is wrong. What is the reason? Can anyone tell me what is the reason? This is not mod 6 counter. This counter is not mod 6. What is the reason? Why this counter is not mod 6? Why this counter is not mod 6? What is the reason? Please tell me. Why this counter is not mod 6? Do you remember this clear? This clear is asynchronous. This clear input, this is asynchronous. Correct? This clear input is asynchronous. This clear input is asynchronous. Yes or no? This is asynchronous. This clear input is asynchronous. What it means? What it means? It does not wait for the clock. It does not wait for the clock. Yes or no? It does not wait for the clock. So this clear input is asynchronous. What it means? It simply means it does not wait for the clock. It will do its work immediately. It will not wait for the clock. Asynchronous clear input, it simply means, okay, does not wait for the clock. It does not wait for the clock. It does not wait for clock age. It does not wait for the clock age. Okay, so what it will do? It will do its work immediately. It will do the work immediately. Are you getting what I am saying? Please tell me. So tell me what I am trying to say. What I am trying to say. This is what I am trying to say. Okay, when the input will become, when this will become 1, when this will become 1, then what will happen? Immediately what will happen? Tell me. Immediately what will happen? When Q0 equal to 1, Q2 equal to 1. Immediately what will happen? Tell me. Immediately what will happen? Immediately what will happen? Immediately they will become 0. Immediately all of them will become 0. Correct? Yes or no? Immediately what will happen? Immediately all of them will become 0. All of them will become 0 immediately. Correct? Yes or no? All of them will become 0 immediately. Okay, immediately all of them will become 0. So can you see the count 5? Can you see this count 5? See, okay, from 0 you will go to 1, from 1 to 2, from 2 to 3. So I can say this will happen. Okay, this will happen. You can notice that this will happen. Okay, this from 0, 0, 0, you will go to 0, 0, 1. From there you will go to 0, 1, 0. From there you will go to 0, 1, 1. From there you will go to 1, 0, 0. Now, Now what will happen? For a moment this will happen. For a moment this will happen. For a moment this will happen. Momentarily glitch. For a moment this will happen. Remember, this will happen for entire cycle. Yes or no? For one cycle. For one cycle this will happen. After every cycle this will change. Correct? Yes or no? Do you agree? Please tell me. For every cycle this count will remain. Remember, this count will be there for one cycle. For one cycle this count will be there. Okay, this count will also be there for one cycle. But you can notice, for a moment this will become 5, immediately this will become 0. Immediately this will become 0. Immediately this will become 0. So if you notice, actually it's like this. It's like this. Okay, remember, this is momentarily. Please understand, this is just a moment. For a moment this will happen. For a moment this will happen. Okay, and so that is the reason. Finally, what is the answer? So tell me, what is the answer? So what is the answer? So answer is mode 5 counter. Answer is mode 5 counter. Is this point clear to everyone? Please tell me. Is this point clear? So this is actually mode 5 counter, means from 0 to 1 and so on till 4 and then 4 to 0. And remember, that is unwanted. Unwanted is this 5, 101 equal to 5. This was unwanted glitch. Please tell me, is this point clear to everyone? This question, this is a very nice question. Please tell me, did you understand this question? Please tell me, did you understand this question? So take care when there are clear inputs. Yes or no? You should take care. Remember, this week do when we have unwanted signal. Okay, when this is basically unwanted signal. For the unwanted signal, okay, for the unwanted input, we put this. We do the clear. So, okay, take care about this clear input. Is this point clear to everyone? Please tell me. So you can notice the number 5. What will happen to the number 5? What will happen to the number 5? The number 5 is displayed for a very small moment. The number 5 is displayed for a short moment of time. Okay, so your counting is like this. From 0 you are going to 1, then you are going to 2, then you are going to 3, then you are going to 4, then you are going to 4. Then for a moment, actually you are going to 0. Actually you are going to 0. For a moment there will be 5. For a moment there will be 5. For a moment there will be 5. Okay, and immediately it will become 0. Okay, so I can say this is a mode 5 counter. So in which situation you should take care? Please tell me. In which situation you should take care? This is a very important note I am telling you. In which situation you should take care? Okay, in this preset comma clear. Preset comma clear inputs. Okay, these preset comma clear inputs, these are asynchronous inputs. These inputs are asynchronous inputs. These are asynchronous inputs. What that means? Asynchronous inputs means they don't wait for clock. Okay, they don't wait for clock. They don't wait for clock. Okay, so you should take care when these are, okay, I can say when, okay, so when these are when these are asynchronous input, then take care. Then you should take care. Okay, now let's see. Now let's see this question. So tell me, what is the answer? So let's see this question number 13.18. This is question from Fundamentals of Logic Design, okay, by Charles Roth. So this question is there. Now, did you try this question? In this question, what we have? In this question, one new thing is there. In this question, what we have? We have external input. Where is the external input? Tell me. Where is the external input? And there is output. You can notice this is the external output. Okay, in this question we have external input. Also we have external output. In this question, what we have? We have two things. We have external input also. So you can notice we have external input also. This is your external input. Can you notice this is the external input X? And you can notice this is your external output Z. Okay, so these two things we have. So this is a question in which we have external input. Also we have external output. So two things we have. Okay, will the analysis change? Because of this, remember this is your external input. Because this is your external input. This is your external input, and you can notice this is your external output. This is the external output. So tell me, will the analysis change? Will the analysis change? No, the analysis will be same. It is just that you have to take care of this input X also. You have to take care of this input X also, and you have to find this output also. Okay, you have to find this output also. So okay, the analysis will not change. Remember, analysis will not change. The same analysis you will do. So what is the same idea? The same idea you will do. What will be the idea? The same idea you will apply, that this is your current state. This is your current state. From this current state, you will find what is the next state. Okay, from the current state, you will find the next state. From the current state, what you will do? You will find flip-flop input combinations. You will find flip-flop input combinations. I can say, okay, flip-flop inputs. Flip-flop inputs you will find, and from flip-flop inputs, you will find the next state. Okay, this we do when there is no external input. This we do when there is no external input. When there is no external input. So when there is no external input, then we do this. In case of external input, what will change? In this diagram, when there is external input, when there is external input, in this diagram, what will change? When there are external inputs. So when you have external inputs, you can have any number of external input. So when you have external input, when there are external inputs, okay, then in this situation, what will happen? In this situation, from current state, comma, external inputs, only this thing will change. Yes or no? Only this thing will change. So what will change? Only this thing will change. Current state, comma, external inputs, comma, external inputs. Only this thing will change. In this diagram, only this thing will change, that current state, comma, external inputs. From that you will find flip-flop inputs, and from that you will find next state. Only this thing will change. Did you understand? Please tell me. Please tell me, did you understand? Only this thing will change. Nothing else. Only this thing will change. You can notice when there is no external input, then from the current state we are finding the flip-flop inputs, and from flip-flop inputs we are finding the next state. This is what we are doing. Okay, this is what we are doing. Now you can notice when there are external inputs, when you have external inputs, then only this situation will change. Like current state, comma, external inputs. From these I will find out flip-flop inputs, and then I will find the next state. Only this will change, nothing else. Tell me one more thing. So if I want to write the output equation or state equation, if I want to write a state equation, then what will be this function of? This state equation, when there is no external input, when there is no external inputs, then what will happen? When there is no external inputs, then what will happen? Then this next state is a function of present states. Correct? Yes or no? This next state is a function of present states. I can say next state will be function of, remember, next state will be function of present states. I can say, so your next state Q plus, that will be a function of present states. That will be a function of present states. So now when you have external input, then what will change? When you have external inputs, then what will change? Then the next state will be function of present states, comma, external inputs. Only this will change, correct? Yes or no? Please tell me. Is this clear to everyone? Please tell me. So next state will depend on present state and external inputs. It will depend on these two. And similarly, you can find the output equation. The output equation will depend on whom? The same situation will happen. Output equation, when there is no external input, when no external input, then what will happen? Okay, like when there is no external input, then what will happen? So the output equation, let's assume you have output. So what will be the output equation? That will be function of present states. That will be function of present states. Okay, now similarly, if you have external inputs, if we have external inputs, then in this situation what will happen? Then only this situation will change. I can say the output will be function of present state comma external inputs. Only this will change. All the other things are same. So I hope this point is clear. Now let's solve this question. This is a very easy question. So in this we have this x. So you have to take care about this x. So basically now what will happen? There are two D flip-flop. Let me call it D1. Let me call it D0. Okay. So you can call it D1. You can call it D0. Okay. And this is your x. So basically there is something called x. Remember, we have x, and we also have this x we have, and we also have these two states. Okay, I can call it q1, I can call it q0. Let me call it q1, let me call it q0. Already the name is already there, so it is already called q1. So let me call it d2, let me call it d2, and this is already q2, this is already q2. Okay, now you can notice that, so you have q2 q1, you have q2 q1, and this x is there. So from this what you will do, you will find the next state, you will find the next state you will find. And what are the inputs? The inputs are your d2 d1. These are the inputs. Only this will change, only this situation will happen like this, and your output is z, and your output is z. You can notice the output is z. Okay, so this is the current situation. Now tell me, now what will happen? So we have external input. Remember, this x is the external input, and these are the present states. So this is what we have. So I can say this is your external input. This is the external input. This is the external input. You can notice this is your present state. These are the present states, and you can notice these are the next states. These are the next states. What will be the next states? And these are the flip-flop inputs. And these are the flip-flop inputs. These are the flip-flop inputs. Okay. So now let's find out. So you first of all, you tell me what is the equation? What is the D1? Tell me what is D1 in this. What is D1? D1. Remember, this is Q2. Remember, this is Q2. Okay, so what is D1? This is Q2, and this line, this is coming from Q1 dash. This is Q1 dash. Okay, you can notice this Q1 dash. So this is, I can say this D1 is Q1 dash or Q2. This is Q1 dash or Q2. Okay, what is D2? Tell me what is D2? D2 equal to X. Can you notice D2 equal to X? D2 is the same as X. This D2, that is same as X. Okay, so D1 is this. I can say. So there will be how many rows? How many combinations will be there? Tell me how many rows will be there? Please tell me how many rows will be there in this truth table. In this table, how many rows will be there? There will be total 8 rows, because okay, you can notice the input x can be 0. So when the input x is 0, then the present state can be like this. Then the present state can be like this. Okay, then the present state can be like this. And similarly, when the input x is 1, then also the next state can be like this. So total 8 rows will be there in this table. Total 8 rows will be there. What is the reason? The reason is this. Okay, total 8 rows will be there in this table, and the reason is this. Because of this you are getting the total 8 rows. Total 8 rows you are getting because of this. Okay, now you tell me what is D2? D2 is already given to you. D2 equal to X. D2 is same as X. Remember this D2, this is same as X. This is same as X. D2 is same as X. This is same as X. And what is D1? D1 is Q2 or Q1 bar. D1 is Q2 or Q1 bar. Okay, Q2 or q1 bar, or q1 bar, okay, q2 or q1 bar. So this will be d1, correct? Okay, very simple. So now you have d1, you have d2. Now tell me, if you have d2, then what will be q2? Remember this, in d flip flop what we have? In any d flip flop what happens? In any d flip flop what happens? In any d flip flop what happens? Tell me. In d flip flop, so in d flip flop what happens? The next output is same as your d. Okay, next output is same as d. In d flip flop this happens. Okay, whatever is the value d, whatever is this value d, whatever is this value d, that will become your next output. Okay, so whatever is this value, that will become your next output. So this value will become your next output. So next output is same as d. So you can notice if your d2 is 0, okay, so this will be 0, 0, 0. This will be same as d2. And this will be same as d1. And this will be same as d1. Okay, so this is your this is the idea. Now you can make the state diagram, correct? Yes or no? Now can you make the state diagram? You can very easily create the state diagram, but before that you also find out the output. You also find out the output. What is this output? Can anyone tell me? This z, what is this z? This z is equal to q2 dash, or okay, this z is equal to q2 dash or q1. This z is equal to q2 dash or q1. So first you find this z. Z is q2 dash or q1. Q2 dash or q1. Okay, so this will be q2 dash or q1. So I can say this will be q2 dash or q1. Okay, so this will be your z. So you have z also. Now you can write all the equations. Now you can very easily create all the equations. So first of all you can create the state diagram. So tell me what will be the state diagram. Now you can create the state diagram. In the state diagram what will happen? First you tell me, in the state how many bits are there? In any state how many bits are there? In any state how many bits are there? Tell me, in any state how many bits will be there? You have 2 flip flop, so only 2 bits will be there. Okay, or you have only 2 flip flop, so only 2 bits will be there. You can notice. So these are the states. Remember the state is like this. In the state diagram basically these only 2 states you have. You have q2, you have q1. Okay, so 0, 0. What is the next state? It will depend on x. It will depend on x. Okay, I can say it will depend on x. Or state will only have 2 bits. State will only have 2 bits. Correct? Is this clear? State will only have 2 bits. I am talking about state. The state of circuit, the state of sequential circuit. What is state of sequential circuit? Tell me. State of any sequential circuit, what is that? State of any sequential circuit, what is that? That is your flip-flop output combinations. That is a flip-flop output combinations. That is flip-flop output combinations. Is this clear? Flip-flop output combinations, that is state. So you can notice in the state you have 2 bits. Okay, from this state 0, 0, where you will go? From this state 0, 0, where are you going? From this state 0, 0. From this state 0, 0, where are you going? You can notice if x is 0, I will go to 0, 1. If x is 0, I will go to 0, 1. Okay, so from this state, I can say from this state, if x is 0, I will go to 0, 1. If x is 0, okay, remember x equal to 0, I will go to 0, 1. So if input is 0, this is your, I can say this is your input. If the input is 0, then I will go to 0, 1. What else? If input is 1, I will go to 1, 1. If input is 1, then I will go to 1, 1. If input is 1, then I will go to 1, 1. If input is 1, I will go to 1, 1. Okay, next, tell me, after that, if your state is 0, 1, then where I am going? If state is 0, 1. If state is 0, 1 and input is 0, I will go to 0, 0. From state 0, 1, if input is 0, I will go to 0, 1. Okay, if input is 0, remember, if input is 0, I will go to 0, 0. I will go to 0, 0. Next, from state 0, 1, if input is 1, I will go to 1, 0. If input is 1, remember, if input is 1, I will go to 1, 0. if input is 1. After that, okay, from this state 1 0, from this state 1 0, from this state 1 0, if input is 0, I will go to 0 1. If input is 0, if input is 0, I will go to 0 1. And from this state, if input is 1, I will go to 1 1. If input is 1, I will go to 1 1. Next, after that, from this state 1 1, from this state 1 1, if input is 1, I will go to 1 1. If this input is 1, I will go to 1 1. And this, if this input is 0, I will go to 0 1. If this input is 0, I will go to 0 1. Is this clear to everyone? Please tell me. Is this point clear? Did you understand this state diagram? How are we creating the state diagram? Remember, state means flip-flop output combination. State, what is the state of sequential circuit? State of a sequential circuit, what is that? State of a sequential circuit, that is flip-flop output combination. That is flip-flop output combination. You have two flip-flop. You have two flip-flop. Only two flip-flop you have. This flip-flop, this flip-flop. Only two flip-flop we have. Remember, please understand, very simple point. You have only two flip-flop. So every state will have 2 bits. Because state of a circuit, state of this circuit, this is your circuit. State of this circuit, that is flip-flop output combination. So state of a sequential circuit, that is flip-flop output combination, there are only 2 flip-flop. So every state will have 2 bits. So you can notice your states are these. Your states are 0 0, 1 1, 1 0, 1 1. These are the states. Now you can notice what is happening. In this state 0 0, if input is 0, I will go to 0 1. In this state 0 1, if input is 0, I will go to 0 0. So this is the input. Did you see this? Okay, is this clear? This state diagram. Is this Millet machine or Murray machine? Is this Millet machine or Murray machine? Is this Millet machine or Murray machine? This is Millet machine or Murray machine? This is a Millet machine, correct? This is a Millet machine. So they can ask you, is this Millet machine or Murray machine? This question they can ask you. Okay, they can ask you, is this Millet machine or Murray machine? So this circuit, remember, this circuit is Millet machine. Okay, this circuit, this particular circuit is Millet machine. This particular circuit, this is a circuit for Millet machine. Okay, is this clear? So all the points are they clear? We have seen the state diagram. This is the state diagram. Okay, this state diagram we have seen, and we have seen. Okay, and you also tell me the next state equation. First, you tell me the output equation. Tell me the output equation. Output is your Z. Output is Z. So that will be function of Q2, Q1, and also your X. That will be function of present states. These are the present states. So that will be function of present states. Okay, and also your external input. So tell me, what will be the equation for Z? Can you find out the equation for Z? So equation for Z you can very easily find out. You can make the K-map. Okay, you can create the K-map. So the K-map you can create Q2, Q1, X. So you can just easily create the K-map. So this will be the area for Q2. This is the area for Q2. This is the area for Q1. This is the area for X. Now you can make the K-map. This is your Z. This is the output. Okay, just focus on the output. So you can notice. So Q2, Q1, X. Or I can say X, Q2, Q1. You can take X, Q2, Q1. Okay, no problem. You can take X, Q2, Q1. You can take like this. You can take X, Q2, Q1. Okay, so you can, this is the area of Q2, X. This is the area of Q2. This is the area of Q1. So you can notice here, apart from these two, okay, 2, 6, that is 0. Only 2, 6, it is 0. So here 1, 0, 1, 2, 3, 0, 1, 2, 3, 4, 5, okay, 6, okay, so this will be your K-map. Your K-map will be this. And from this K-map, you can create one, this will be Q1, okay, you can make one cube like this, and you can make another cube like this. And you can make another cube like this, that will be your Q2 bar. So tell me Z equal to what? Z equal to Q1 or Q2 bar. z equal to q1 or q2 bar. Okay, but actually, okay, it is already given, right? Yes or no? Actually, state equation, you don't need to find the output equation. The output equation is already given to you. The output equation is already given to you. The output equation is already given to you. So you can notice this output equation, you can from the circuit also you can find. This output equation you can find from the circuit also. So this q2 bar or q1. So this output equation you can find from the circuit also, and you can find from this table also. So from this table also you can find the output equation, that will be q1 or q2 bar. And similarly you can find the next state equation. Similarly you can find what is the next state equation. This next state equation also you can easily find, like what is q2 plus, that will be a function of x comma q2 q1. And similarly this q1 plus, that will be a function of x comma q2 q1. Okay, so like this you can do. You can use, using the K-map you can find. Use K-map. So like this is the question. Please tell me, did you understand this question? Please tell me. We have done the complete analysis of this question. We have the flip-flop input. You can notice we have everything. Okay, you have flip-flop inputs. These are the flip-flop inputs. These are your flip-flop inputs. So if they ask you what is flip-flop inputs, these are the flip-flop inputs. So we have flip-flop inputs, and you can notice we have this output equation also. This output equation is this. Here is your output equation. This is your output equation. And you can notice we have transition, output labels, transition graph. So this is transition graph means state diagram. State diagram we have created. Okay, so like this we have done. Can you notice what this circuit is doing? Now the question is asking what is the circuit, this circuit, what this circuit is doing. What this circuit is doing when it is producing output 0. What this circuit is doing when this circuit is producing output equal to 0. So when output is 0, then what this circuit is doing. So remember your state diagram. From the state diagram you can see. So when your output is 0, then what this circuit is doing. So what this question is, give one sentence description of when the circuit produces an output 0. So when the output will be 0, tell me. Output will be 0. In which situation output will be 0? When q1 is 0, q2 is 1. Okay, so you can notice when z equal to 0, it means what will happen? q2 equal to 0 and q1 equal to 1. You can so you can notice q2 bar or q1, q2 bar or q1, q2 bar or q1. So it will happen q2 bar or q1. So I can say this will be 0, this will be 1. So in this situation, when you have this situation, in this situation what will happen? You will produce output z equal to 0. So the output z equal to 0 you will produce when your state is this, when your next state is this, I can say. Okay, so from this table, from this state diagram, what you can check? You can check when is your output, when is your next state 1 0. When is your next state 1 0. So when is your next state 1 0. So tell me, when will be your next state 1 0. When will be your next state 1 0. In which situation your next state will be 1 0. So when is next state 1 0. So you can notice when your next state is 1 0, okay, then in this situation you will produce output. Then in this situation what will happen? Then you are producing output 0. And if you are producing output 0, it means next state is this. So this is the simple point. Now when the next state will be 1 0, the next state will be 1 0, either from this state you are getting 1, okay, or I can say from this state. So your next state will be 1 0 only when, okay, you are going from here. So I can say from this state you are, okay, you are getting 1. You are getting 1 and you are in this state. Okay, And so from the initial state, if you see how to find out the description, how will we find out the description? So from this state, if 0 comes, you go here. If another 0 comes, you go here. When you will produce output 0, when you will produce the output 0, this output 0, when we will produce, okay, so in this I am saying 0, 0. After 0, if 1 comes, you go here. Ending with 0, 1, can I say? Yes or no? Ending with 0, 1. Ending with 0, 1. Because if your input, basically this x, when this will happen, when your next state will be 1, 0, when you are ending with 0, 1, you can notice if you are ending with 0, 1, then you are going to 1, 0. From any state, from this state you are not going, from this state on 0, 1, then 0, 1. Okay, anyway, okay, I will check it. I will check it. What will be, like, what can be one sentence description? See, we have seen everything. We have also seen this state table, outputs equation, okay, input equation, the analysis, everything we have seen. But I will check what can be the one sentence description for this question, what it can be. That I will check. Okay. So anyway, let's move on. Let's see this. So can you try this now? Can you try this question? Did you try this? Again, we have external input and output. We have external input, we have external output. You can notice in this question, we have this external output. So we have external output and also we have external input. This is the external input. So you have external input. So you have external input and you can also see that you have external output. Or I can just simply call it output. Okay, you have external output. So now similar, the same type of analysis you need to do, right? Okay, so you can do the same type of analysis, the exactly same analysis you need to do. So what you will do here, again the same. So you can do this type of analysis, that this is your x and you have two states. So that is q2, q1. So it will be like q2, q1. And okay, then you will find what is your q2 plus, what is your q1 plus. Okay, so this is what you will find. Okay, and you have d2, d1. This is your d2, this is your d1. Okay, so the same analysis we need to do. Remember, the same analysis we need to do. There is nothing change here. So first you tell me what is d2. Just tell me what is d2. Okay, just tell me what is d2. What is this d2? This d2. This d2. What is this d2? What this d2 is? Remember, this is NAND. This is the NAND followed by NAND. What is this NAND? This NAND circuit. This NAND circuit, this is equivalent to AND OR circuit. Yes or no? This NAND circuit, this is actually equivalent to AND OR circuit. So both these circuits are same. So actually here what will be D2? So what your D2 will be? D2 is basically AND OR circuit. I can say D2 is AND OR circuit. Remember, this is D2, this is your AND OR circuit. This is Q1 bar. Okay, this is Q1 bar and you can see this is your Q2 bar. This is your Q2 bar. So it will be like, I can say Q1 bar, X Q1 bar or X Q2 bar. X Q1 bar or X Q2 bar. This will be your D2. So your D2 will be actually X Q1 bar, okay, or X Q2 bar. Is this clear? X q1 bar or x q2 bar. This is your d2. And what is d1? What is d1? D1 is q1 bar. Okay, so you can notice this is your q1 bar and q2. So this will be q1 bar or q2. So these equations we have. Now you can very easily create. So it will be like this: 0 0 0 0. Okay, and then 1 1 1 1. Then you can notice for every combination 0 0 0 1 1 0 1 1. Then 0 0 0 1 1 0 1 1. And then what you will have? Okay, then from this you can find the d2. Remember what is d2? D2 is you can take x out. Okay, you can take x out. So I can say d2 is basically x q1 q2 bar. Okay, x into q1 q2 bar. Okay, you can think like this. So x q1 q2 bar.